In this video, we are looking at zeros of polynomials, and the zero of a polynomial is a point where the polynomial becomes zero as a whole, or where the graph crosses the x-axis. The zeros are also called roots, solutions, or x-intercepts of the function. There are two types of zeros. The zeros might be real, and when they are real, you can actually see them on the graph as x-intercepts, and they may cross. You may, at that point where the zero is, the graph may cross the x-axis, or it might just bounce off, like is happening right here. So those are real zeros, and I can circle these ones down. So that's one of the zeros, that's another zero. However, if you look at this other graph here, I do not see any part of the graph cutting the x-axis or even touching it. So these are imaginary zeros. That's how you can tell the difference. And now let's look at the degree of a polynomial. So the degree of a polynomial is something very important, because the degree helps you to know the behavior, it helps you to know the type of zeros and all that. So a degree of a polynomial of degree n has n zeros. That's one thing you can tell from the degrees. However, you may not be able to tell the type of zeros. You may not know whether they are real or imaginary just by using the degree. So they might all be real, some might be imaginary, or it might be a combination of both. Let's look at some examples, and here I just want us to tell what the degree is and also state the number of zeros. So look at this first polynomial. This here, I see two factors and I see an exponent here. So these factors are linear factors, because x minus 2 would represent the equation of a line, so they are called linear factors. And if I was to expand this equation, I could do that and write it in standard form. But right now I just want to find the degree. So one way to tell the degree, I can take x, this is x, and it's going to be raised to power 2. And this is x, it's going to be raised to power 3. If I add those two exponents, I'm going to get 5. So the degree here is 5. And the number of zeros from the statement here is going to be 5. But another question I could ask myself, can I be able to tell whether the zeros are real or imaginary? For this particular example, it's very easy to do that, because if you make each of the factors equal to 0 and solve them, and I could do that. If I look at the first one, x, if I equate x minus 2 to 0 and solve it, so x minus 2 is equals to 0, then I would get x is equals to 2, positive 2. If I did the same for this one, I would get negative 5. And I know these are two zeros. They don't correspond with the degree, but this is because I need to consider how many times the 0 is repeated. Like 2 is repeated 2 times, and negative 5 is repeated 3 times. And that's from these exponents, because they represent the multiplicity, or how many times the 0 is repeated. And remember, if I add these ones, I get 5, which corresponds to the degree. Now, the second example here, this one, if I look at it, it starts from the highest exponent and just keeps going down, 832. So this one here is in standard form. This one is very easy to tell the degree, because I just need to look for the highest exponent. So this is 8. But as you can see, it's not easy to tell what the zeros are, whether they are real or imaginary. I cannot tell from here. It's not easy using the standard form. I just know the number of zeros are 8, but I don't know how they look like. So that's the difference between the two. So this form, however, helps me to find the y-intercept. I know the y-intercept is going to be 10. The first one, I cannot be able to tell the y-intercept, but I can be able to tell several things when it is in factored form. I can tell the behavior of the graph at the intercepts. I can also be able to tell, I can be able to tell what the zeros are easily. Okay, the next one, this one is expanded out. The only difference is that it's not in standard form. So the highest exponent is not the first one. So the degree for this one is 6. So the degree is 6. So the degree is 6. And the number of zeros are just going to be 6. Here, let's look at the complex conjugate theorem. And it says complex roots occur in pairs. In other words, given one complex root, we can state that its complex conjugate is also a root. So here, I'm talking about complex conjugate. So what does this mean? If you look at this here, a plus bi, a is the real part, bi is the imaginary part. And the other thing I want you to see, this is a plus bi, this is a minus bi. This pair is called the complex conjugate. That's complex conjugate, both of those. One is a complex conjugate of the other. So look at this one here. If this is a root, what is the other root of the polynomial? So what other root do I know has to be there? And this is going to be the complex conjugate. So the opposite, so it's going to be plus 2i. And let's look at the other one. What is the minimum degree of the polynomial? And these are the zeros given. Whenever I see an imaginary zero, my first thought is, do I have two of them? If I don't have two of them, I need to find the other one. So this is what I have. I need to find the complex conjugate of this one. So the other zero is going to be negative 4 minus 2i. And now I can be able to count the zeros 1, 2, 3, 4, 5. So I know the degree is going to be 5. Okay. The next one is asking me to write the factored form of a polynomial, and the zeros are given. Once again, I check, do I have all the zeros? And I see a 4i, so I know I'm missing one. So the other one is going to be 4, negative 4i. So I could actually be able to tell the degree of this function, 1, 2, 3, 4, the degree is 4. And I can be able to write the factored form. So this is going to be f of x is equals to x minus 1, x minus 2, and the other one is going to be x minus 4i, and x plus 4i. And remember, I could expand this. If I expanded, I could expand these ones. For example, I could expand it more. So x minus 1, x minus 2, and then x minus, when I FOIL these ones, I'm going to get plus 16, plus 16. So this is going to be x squared plus 16. So when I solve this part here, That's how I get these two. And maybe you are asking yourself, where do these kind of zeros come from? And you can see this last part here. If you consider it, if I consider this one, if you solve it, if you solve this one, so you have x squared. I move the 16 over to the other side, negative 16. I find the square root of both sides. I remember plus or minus. That's how I get x is equals to plus or minus 16. And I also have negative 1 if I separate the negative. And remember, the negative 1 square of that represents I. So that's how we get plus or minus square root of 16 is 4, then I. So now let's look at multiplicity of zeros. And what does multiplicity mean? This is how many times a root is repeated. For example, this, if I have this polynomial, I can see x minus 3. If I made it equal to 0 and solved it, I get 3. And this exponent tells me 3 is going to be repeated 4 times. So negative 1, if I solve this one, that has a multiplicity of 3, so repeated 3 times. 1 repeated twice. So if I sketched it, let me see how it behaves. Each intercept behaves, or each 0 behaves. Look at negative 1. I know the multiplicity is 3, so see what is happening. It crosses, but it's flattening as it crosses. So I know 1 is even, has even multiplicity, so it bounces off. It's going down and then changes direction and starts going up. Okay, 3, what do I know about 3? 3 is also bouncing off, but the kind of way it bounces off is a little bit. See, this was x squared, this is x power 4. This one flattens a little bit. Flattens a little bit. Okay, so now let's look at the next one. So this, I see the zeros, x minus 1. X minus 1, this one just crosses. The multiplicity is 1. Then I go to the next one. When it's squared, this one is bouncing off. So kind of the same behavior we had right here. Okay, and now I only see 2 zeros, this one and this one. If I don't see the other one, it must be imaginary. And I can be able, I have to get the other zeros, I have to solve x squared plus 2 is equals to 0. So x is equals to minus 2. So x is equals to plus or minus square root of negative 2. When I see the negative, I know that's I. So that's how I get x is equals to plus or minus square root of 2i. That's how I get these imaginary zeros. Let's look at some statements over here. So the first one says real zeros of a polynomial are its x intercepts. And I see that that's true right there. Algebraically factor the polynomial and set it equal to 0 to find the zeros. Okay, the next one. Imaginary numbers do not appear on the graph. The only way you can find them is by solving for x algebraically, just like I did here, to get those roots. Zeros with even multiplicities, what happens? The graph touch or are tangent to the x-axis at these values, and I see it here. Touch, or the bouncing off, or are tangent. Okay? Zeros without multiplicities like 1, 3, they cross or intercept at these values. In this polynomial, let's look at how to write equations of a polynomial. And if a polynomial of lowest degree p has the following zeros, then we can write this polynomial in this form. This is called the factored form. These are the linear factors. I want you to see that they have a value a here, which is the stretch factor. And that's what we are going to, when we write the factored form, we need to include this a. And the powers of these exponents, we can be able to determine them from how the graph is behaving at the intercepts. Is it touching or bouncing? So, and then we are going to find the value of a. To find the value of a, you want to use another point, and just make sure you don't use the intercept. You could use the y-intercept, or you can just use, but don't use the x-intercepts. You can use this point, or you can use this point here. So let's work it out. So here, I'm going to start by writing the zeros. So one of the zeros is right here, and this is -1. And I see the multiplicity is equals to, I know it's not 1 because it's flattening. So the minimum it can be is 3. Because it could be 5, I do not know, but the minimum possible is 3. Okay. The next one is right here is 2. And I see it's even because it's bouncing off. So, but the minimum it can be is 2. So I'm going to write 2. And the minimum, the multiplicity is going to be 2. So what factor goes with this one? This 0. To write the factor, just going to be x. I flip the sign, so it's going to be +1. And this is going to be x minus 2. Don't forget the multiplicities. This is 3, and this is 2. The degree of this polynomial is 5. Now I'm going to write f of x is equals to a, then x plus 1 cubed, and x minus 2 squared. And now I just need to pick another point except the x-intercept. I'll just pick this one, 0, 4. I think this is going to be easy if I do that. So y is 4. So this is going to be, and I know x is 0. So so x is 0. So that's 0 plus 1 cubed. And then 0 minus 2 squared. And what am I going to get? So this one is just going to be 1, and this is going to be 4. So that's going to be 4a is equals to 4, and a is equals to 1. Remember, if I used another point like 1, 8, I should get the same answer, and you can try that for a. So now I can write my equation to f of x is equals to 1. So this is going to be x plus 1 cubed and x minus 2 squared. So this is the equation of the polynomial. Now here, let's look at the effects of vertical transformation on zeros of polynomials. So here I have a polynomial. I see the equation, factored form, and the degree is 5, and these are the zeros and the multiplicities. And let me look at this graph closer. From the look of it, I see I have 2 real zeros. That's one of them, and that's one of them. What would happen if I shifted the graph using the value k, where k is an integer? And that means I can move it up or down. if I shifted this same graph up 2 steps, see what happens. The 3 was a 0. I shifted it up. Now it's kind of floating. And I see at this moment, I have 1 real 0. 1 real 0. Because the others are now imaginary just by adding that k factor, just moving the graph up. What about if I shift it down? Remember I had 2 zeros before, originally 2, 1, 2. Now if k is 3, if I just put negative 3 on this equation, see the graph moves down and now you have 3 zeros. I have 3 real zeros. So 3 real zeros just by shifting 1, 2, 3. So that's how you can be able to change the nature of zeros. Remember, you still have the same number of zeros, but you're just changing them to imaginary